Get going. So again, this is Mr. Hayden. This is chemistry. This is week 12. Hope everyone had a good break. Speaking of break, that's a few things that we're going to be talking about. How was your break? I know it's hard for the people on the internet to answer that question, but some of the other people, can probably answer it in here. So how are you guys' break? Good. Just good. We're doing good. Okay, so I got a good. That's good. What else? What did you guys do? Anything fun? Someone was sick. She literally was dying. Yeah. Literally. So I think it's figuratively, but we'll literally just make it so bad. Or what else? So sick. Fine. How was yours? Okay. Okay. Was it just okay with an O and a K or O-K-A-Y? Just no and a K. So not as good as an O-K-A-Y. How was yours? Fine. Huh? She had homework to home. That's perfect. We're going to be talking about that pretty soon. It's fine and dandy. Fine and dandy. Don't use that anymore. Long. How was yours? Great. Great. What did you do? That was so great. Yes. All right. We got great sleep. We have homework. Okay, just the O and the K. We have sick. We had fine. Went to the beach. No one's talking to you. You're not in my class. I'm just kidding. I'm looking at the computer. Talking to the computer. All right, so I'm glad that your break was good. Everyone had a good break. I kind of just worked on some stuff around the house for the little guy. So that's pretty much all I did. Family stuff here and there, stuff like that. One thing I do want to point out, guys, is that there's only about 8 more weeks of school. That's it. It's really not a lot. Sounds like a lot. But it's only like 40 days, minus a few days here and there. So, and then Long is smiling like I've never seen her smile before in my life. She's like, 40 more days left until I don't have to see Mr. Hayden anymore. See, she's trying to laugh, but she knows it's true. It's okay. I wouldn't want to see myself if I didn't have to either. That's why I avoid mirrors. All right? So 8 more weeks left of school. So what does that mean? Science notebook should be going. If you're new, or if you're listening to this and you're new and you came, which I don't think this class really anyone new for the last 3 or 4 weeks or so, you need to basically make sure your science notebook is from the beginning of when you started, going on forward. All the units are open. Remember the semester final test thing, whatever, it's cumulative, so your science notebook would be a perfect thing to use for the test, because all of your notes should be in it. The goal is every answer should be in your science notebook somewhere. If it's organized properly, it's easily to access. It should be your book. So when you take the semester test, you shouldn't even really need it, but if you do, it's there. And there you go. Happy, happy, happy. Joy, joy. All right. No one else got that. Did you get that? No, you're too young. Good job. All right. Another thing, too, is grades. I know a lot of people told me, I'm going to be working during this break, and I'm going to work, and I'm going to do a bunch of work and bring my grade up, and oh, yeah. Then Monday came around, and they're like, wait, I'm off for a week. I shouldn't have made that promise, Mr. Hayden. Phew. And then I looked, and guess what? I didn't have to grade that much stuff for this class, strangely enough. So the thing is that if you do have a not smiley face grade, you had your chance this last week to bring it up without me bugging you. If for whatever reason you come to me now and say, Mr. Hayden, can I make a blah, 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 blah? I'm going to say, go ahead. Can you help me? No. Lost the chance. If you don't try on your test and you don't try in class, you have to do things more on your own independently, unfortunately. So if you need help, there's a book there probably, some sort of an internet, maybe some sort of a web page, and you can work on it. If you did work, and I check that you worked during the break, and you have a question, I'll be more than happy to help you on any past work. So there you go. All right, so let's keep going. Okay, so today's session we're going to talk about thermochemical reactions, heat during changes of basically a state of matter, which is, that one's the easiest one of all these. It's like, I don't even know why I have to show you this, but I'm going to have to do it anyways. And then Hess's law, which is relatively annoying because it's an easy thing. It's just hard to explain and for hopefully to get it. So what I did again is I put in front of you the examples that we're going to be going over. And with the examples that we're going to be going over, hopefully we'll help understand these a little bit better. Again, it all comes down to equations. It all comes down to having a bunch of givens, one of them not given to you, and calculating out the answer. That's all it comes down to. All right? So let's get going. So this is just in general. Thermochemical reactions, it's showing you it right there on the, whoa, just kidding. There you go, sorry. I accidentally pushed the wrong button. All right, so up on the screen it says gasoline combustion produces energy. We all know this. I mean, you put gasoline in your car and it moves, hopefully. Yes? Yes, put gas in there and it goes forward, hopefully? Did you get here with gas? Not today. Not today? Well, it would go forward, just not very efficiently. So what happens is, when you put gasoline in there, it changes into a chemical, it changes from one chemical to another, and based on the reaction, it releases or produces energy in this case. So this is the equation, if you ever really cared, of what gasoline is. You add gas, you add oxygen, it equals carbon dioxide, water, and energy. Okay? So, and this is the energy output right here. So it actually releases or able to produce that much energy. A couple things to point out here is that endothermic and exothermic. Endothermic are going to be positive, so if it's sucking in energy, it's going to be a positive answer basically. If it's releasing energy, it's going to be a negative. And since it is releasing energy when you do combustion, that's a negative right there. Okay. So this is just in general, kind of gasoline makes you go forward, produces energy. What we're going to do, I know it's super simple, but what we're going to do is kind of have to figure out how to calculate those changes in heat. That's what basically today is. And how to calculate that based on certain information. Okay, so if you look right here, there's important notes about the thermochemical reactions. So as you're actually changing the states, you're seeing right here that this is one equation, and what's happening is you're actually changing this gas into a liquid. Okay, so in this case it's actually going to be a little different. You're having two reactions take place. You're having this reaction creating a gas, and then this gas then becoming a liquid. In this case, what you do is, since this energy right here is released, as well as this energy is also released, you put them together. You add them together. That's why the total energy for both of them is added up to negative 572. Basically what's happening is there's a change in matter, the state of matter. No, I'm sorry. There's a change in the composition of matter. Then after that, it's changing the state. And since it's changing state, you just combine them. Come on. All right. So on your piece of paper, I actually cut and pasted that information on there. So it says a commercial hand warmer, you know those things that you put in your hand when you go to the mountains to make it so it's like super duper warm. Not really, because they last like 20 minutes and then they go away, then you're like, have just a big thing in your glove that doesn't work anymore. But it contains 100 grams of iron and warms according to the thermodynamic equation shown here. So look at it, it's giving you an equation then. It's a given. This equation right here is the equation that follows. You're not like full chemical engineers. You don't have to actually calculate all this. It's going to be given to you like this. So the question on the right says, use the data from the text on the left, which there it is. If oxygen is at excess, which means you're not constricting oxygen at all, how much heat will the hand warmer produce when all the iron is oxidized? So take a second and just read it, take it in, okay? Just give it a second. First of all, what do we have? I mean, first of all, what's there? Let's read it again. A commercial hand warmer contains 100 grams of iron. Right there we can stop. What is it giving us? What is that? What is 100 grams? What's that word that is in every single equation? Starts with an M. Has to do with weight. Thank you. Math. Don't be afraid to say it. I saw it in your brain coming out. Just let it fall out of your mouth. So we have the mass. Perfect. It also tells you. It also tells you what the molar mass is over here. So let's go ahead and look at the next step. So, come on, Turbo. Okay, so the given. We have 100 grams. The molar mass is 55.8 mass grams. And we also have the change in heat. The change in heat was basically given to us over here. All right, so those are some givens. Now, does everyone remember how to convert let's look at this real quick. Does everyone remember how to convert this stuff? It's probably been a while for that. All right, so basically get the change in heat of just the iron. What they're doing is they're taking the total kilojoules, that's the heat change. So that is what's already given. This right here comes from here. And it's being divided by the amount of moles. Now remember, the amount of moles is the number in front of iron. What number is that? Say it. Take it. Saw the F coming out, and it was either a bad word or the right answer. I'm glad it was the right answer. So right here, there's 4 right here. And so you do your basic division. So it's saying that in this case right here, that you're getting negative 981.5 kilojoule moles of iron change, of the change of iron itself. And so what you need to do from there is you'll then need to actually find out how many moles do we actually have of the substance. They actually were nice enough to give you the exchange, which is right here. You have 100 grams, and so you divide the amount of grams you have by the molar mass, 55.9, which is 1.79 moles. That's how many moles you actually have. Okay, inside that little bag of iron, that's how many moles of iron you have in that little bag of the warmer. Let me know if this doesn't make sense. Just so you know, we did moles before, but sometimes over a week, people forget things, specifically over spring break. So this is how many moles you have. So now I have the heat from just iron, and I also have how many moles of iron. So the next step is some pretty basic math. And this is the equation you want to write down. Q is equal to N change in H. Okay, so it looks like the energy change is equal to the number of moles times the change in heat of that particular substance. So you just multiply them together, it equals negative, means it's giving energy off, remember, from the previous thing, so it's creating heat. Okay, does this make any sense? If it doesn't, it's a question, but if it does, then great. All right, so let's go ahead and move to the next type of equation. Now, this one right here is actually it looks super complicated. It looks, oh my goodness gracious. But it's actually the easiest one of all of them. All right, so it's basically saying this is the combustion formula for methane. Awesome, good for us. So if you're using methane and you're creating a fire with it, this is the combustion. It's taking this hydrocarbon here in a liquid form. You add it to some oxygen. Remember, you need oxygen for fire. And it's creating carbon dioxide and water. That's what gets released. That's not even what the equation is actually asking for. It's actually asking for how much heat has actually been displaced. Like what's the initial start of this thing. So if you take the initial change in heat plus evaporation, it equals the total net change. Well, it gives us the net change here, and it gives us the vaporation here. Okay, so think about that. It just gave us the net, and it gave us the other one. The only thing was the initial. That's really how easy this is. That wasn't hard. That's just enough. So I just want to make sure you point that out. And there you go. So the initial is negative 890 kilojoules minus 88 kilojoules is a total. Where it started at, the initial was. That's it. That's not that hard, right? That's pretty simple. When I first saw it, I was like, oh, wait, that's easy. People aren't even writing it down. That's how easy it is. Okay. Another easy thing to go over, my goodness. Okay. This is the changing of a state from, it looks like ice to steam. Okay? So ice starts at 0. You add heat to a certain level. At a certain point, it starts to liquefy. It goes up, liquefies, hits to a certain point, it goes to another one, and then eventually becomes steam. So ice, from heating ice from negative 100 degrees to 0 degrees Celsius, you're heating it. Nothing's happening. It's just, you're just heating ice, basically. And eventually, the molecules fall off, kind of melt. Literally, they melt. And then they hit to a certain point, they melt at 0 degrees Celsius, which is right here. This is the change of state right here. This is another change of state. And then it stays within that state. So it's ice from here to here, liquid from here to here, steam from here to here. Sorry, give me a second here. Okay. So if I was going to take a piece of ice and go all the way to steam, what do you think I do to all of the heats that I had to add? I mean, I added heat, I added heat, I added heat. What do you think I'm doing when I actually calculate all the heat I put together? What did I do? I added heat, right? What do you think? What math do you think I do? Literally, I just add heat. I add it. It's the math. So if I took, this, come on, Turbo. Sorry, I have to go back to my. So if I took this, plus this, plus this, plus this, plus this, it'll equal the total heat required. Literally, I'm just adding them up. That's it. Now, question, if I had steam and I start cooling it down all the way to ice, literally you can take steam, even steam in this air, and make ice. That's the reason why some people get like ice on their nose and things like that. Like when you're in a super cold area, you'll get ice like on your face, or it'll start condensing on like the wall. There'll be ice there. And you're like, well, how did the ice get there? It's because literally the moisture stuck to it and froze. Now, if I'm starting from here and going to here, what do I do to the energy that I had to put or take away technically? Well, I take all of them and I add them up, but different direction. Not a positive direction, I'm going to a negative direction. Guess what? Come on, Turbo. They're the same answer. They're the same answer. The exact same amount of energy is taken to go from ice to steam, then from steam to ice. It doesn't change. It just changes directions. That's all you're doing is changing directions. Does that make sense? Add them up. Okay. So here's an equation for the heat during change of the process. Now let's look at this. So the given we have here is how much heat is released when 50 grams of ammonia freezes at its melting point. It gives us the molar mass, so it gives us something here. It also gives us the heat change right there. Okay, it also gives us the mass. So look at it, it gives us a whole bunch of stuff. Now, when we actually want to calculate it up, what do we know? Well, we need to convert the mass to moles, just like we did the last time. So I put the mass up top, right here, 50 grams, over, what is the molar mass? Look at them, so nice of them to give it to you right here. They don't even have to make you look it up on the periodic table anymore. Because if you went to the periodic table, you would also have to look that up. By the way, nitrogen is, I believe, 14 is the mass, and 3 hydrogens, 17. So that's how they get that molar mass. They literally add up those little masses at the bottom. of each of the elements. And look at, they went ahead and did the math for you right here. 2.94 moles. That's how many moles you have. Okay, next step. Here's the equation. Q is equal to m, or mass, times change of the heat. So look, so in this case, m is in moles. And then they already gave this to you. Look at them. They're so nice how they give you all these answers already. And then you multiply it across. So that is actually how much heat is released right there. Negative 16.6 kilojoules. So everyone have that equation written down? Q is equal to small m times change of heat, change of heat. And again, they can even have told you, they could have gave you the heat change, and they also could have gave you the moles, and they can literally tell you what is the amount of, what's the heat change. They could tell you to find that, and you just plug everything else in, and you can get the exact same answers. They're giving you two. There's three variables. They're giving you always two, and you just need to be able to calculate the third variable. It's almost every equation that we're going to see. It's just you need to know the equation, you need to know what the mass is, you need to know how to convert from masses to moles, you need to be able to do this stuff. As long as you can do that, you're okay. If you can't, then you got a problem. Okay, so talking about Hess's law. Now when we saw, like when we go back here to this, you can see that each time I'm making a change, right? I'm going from ice to water, water to, we're doing this. But really, when it comes to Hess's law, they don't care what the steps were between. They just care you started here and you went to here. Boom to boom. They want to know from start to finish. They don't care about the steps along the way. It could have went up, froze it, so sit there, up, down, up, down, up, down, up, down. They want to know the end and they want to know the beginning. That's all they want to know. So when you look at Hess's law, this is going to be a little difficult. I'm going to go through it once with you. If it doesn't make sense, we'll do it again. But let's check it out. They don't care again. They want to know the start to finish. They do not care about how many different times it changed, how many they don't care. Beginning, end, it, done. All right? Most of the time when they give you a combustion or give you an equation, they'll give you sub-equations from there that there's heat released, and then you have to be able to reverse the math to get the answer. So this is on the back page of your paper right there. This is there. So you have four of one element, 5 oxygens. You have 4 of the. Basically, you have your products here and your reactants here. Now, there's usually a set of equations below that gives you how much heat change is for each one of those chemical reactions. There's these 3 chemical reactions that took place to allow for this total top, like the big one, to take place. Now what it's going to ask you to do is find the total heat from the change. Something's going to go up, something's going to go down, but there's a beginning and an end. It's asking you to find what that change was from beginning to the end. So, when you go to the next page, you're going to see how they did this. If it's on the product side, the reactant side, they leave it alone. They leave the same direction. If it's on the reaction side, the reactant side, they reverse the arrow to allow for it, saying it can go back and you can change the temperature because of that. You basically make it a positive to a negative, negative to a positive. So let's look at this. All right. Where's it at? Here's the one I want to start with. Where is the one? Where's that bad boy at? Where's the one? Where's the one? Give me 1 second. I'm trying to figure out which one I want to start with. It's this one. Because I'm reversing it, I'm going to be reversing this one right here. We have heat change is a negative. Do you see that? So since I'm reversing it, going from basically it becoming a reactant but not a product, I'm reversing the amount of energy. So what do? I make it a positive. I say it can be reversed back, but all it does, instead of losing the energy, it's gaining the energy. Does that make sense? That's all I'm doing right now. Now, if I look at this, what is the difference between this and that? I mean, just look at it. What's the difference? Just look at those two ones I circled. What is the difference? Thank you. One of the 4 ones and 2. I need to make the one below it into a 4. How do I do that? How do I get to 4 or 2 to become a 4? Or multiply. Thank you. When you're doing like an equation, like you're doing any equation, like you have an x and you want to multiply, you multiply everything across the board, just like in math. So I can multiply this by 2. So 2, 6, 4. Good for me. I just took the amount and just doubled it. Not a big deal. You can do that. That's what they did right down here. It's reversed and multiplied by 2. You can do the same thing to this, which is by 2 as well. You can see there's a 4 here. I'm just making it match that. And this, I'm trying to make it match that. So this one would be by 3. And this would be what? 6. Good for me. And this one here was a 2, right? So it needs to be a 4, 2, 2. By the way, that's the exact same thing that's down here, just so people know. Now check this out. I multiplied this by 2, right? Let me clear this. Let me clear the page. Okay, I multiplied this. Let me get my pointer back. This one by 2, right? Do you agree? Well, guess what? I also have to multiply the energy by 2 as well. All the way across the board. What did I multiply this one by? By 2, right? So, by 2. What did I multiply this by? 2 to 6, 3. So what does that equal? Well, this one here is positive 186.3. This one here becomes 361. And the reason why there's a big plus here, even though this one, right, this one here and this one here are basically positive, they're showing that positive being a change. The positive in front of it indicates there you reversed it and it became a change from a negative to a positive. That's important to visually see. And then this one here, negative, it's this one here. Then literally once you have that, all these start canceling out. And so you got, okay, this one's good, it matches this one. This one's good, it matches this one. So if I bring this down, then I add these up, bring them down. This one comes down. Equals the original equation. Same equation as you started with. You broke it down into simpler chemical reactions. You looked at the change in the heat. You made them match. And then all you do is you add all the heats up. And if you were to add all of those up, the change in heat is negative 906.3 kilojoules for this equation or this reaction. That's something they usually give to you. Like if they're going to give it to you, they just give it to you like, oh, the change reaction is this, like they did previously. Now they're saying, hey, yo, smart person, you need to be able to now take this reaction. If I give you 2, 3, 4 sub-reactions, you should be able to make them match the basically the mama equation at the top. Change the heat as needed. Whatever you're multiplying it, multiply it all the way across, and then be able to add those up at the end. There's some weird ones where there'll be 0.5 of this or 7/20th. It doesn't matter. It's all the same math. The concept never changes. Okay? So I'm just going to jump ahead real quick. So basically, it's not a state, it is a state function, and the path is independent. It doesn't matter. Start to finish. Start to finish. So I'm going to go and have any questions. I'm going to go in and cut the people short on the intranets. So if people have any questions on the internet, what I would like you to do for your essential question is I want you to be able to explain the states of matter from an ice to steam. I want you to talk about each of the additional heats, how much heat. I want to know exactly how much heat is totally needed and what are each of the states called and everything about it. In words, I want you to describe this graph. All right, so go ahead and have a good rest of the day. If you have any questions, ask them. So you guys can go ahead and take off.